Right, let's continue. So, that's about as much as I'm going to say about stack frames for the time being. But the other type of dynamic memory allocation that you're probably more familiar with is using malloc and free. So, we've certainly seen that you can allocate space for an integer or space for 20 chars or whatever, and you can fix up the values of those things at runtime. So all of this stuff happens at runtime. And you could potentially have uninitialized blocks of memory, in which case you've got to allocate values to them, or you can allocate to a limited degree initialized memory using calloc. Notice that annoyingly, the arguments to calloc are different to the arguments to malloc. I mean, probably required because you've got to run through and initialize all the elements, so you need to know how big they are. But still a little bit inconsistent. Alright, so unfortunately, SPIM doesn't give you malloc and free. But it gives you one thing that kind of is useful, and whether it's actually even required or not, yeah, it could well be. I guess SPIM could check whether you're accessing memory outside the range of the allocated data region, but there's a syscall that you can use that will extend the amount of memory in the allocated data region. So the example down here, I want to allocate an extra 20 bytes. Everything in SPIM is done in units of bytes. So I load up the number of bytes I want. I use syscall number 9, which I don't think I put in the SPIM information sheet. I better add it, and then use syscall. And so what that'll do, it'll say, all right, previously the top of dot data was some value, let's say 1000. Now, as far as the process is concerned, the new top value for the dot data region is 1020. So it just bumps it up. So if the simulator happens to check whether you're accessing stuff outside that range, then that'll do. So in some sense, it's a little bit like malloc. It allocates a chunk of space. Unlike malloc, there's no way to free it. So once you've said I want the data segment to be a bit larger, actually I just thought maybe you can free it by calling syscall 9 with a negative value. I hadn't tried that, but someone can try it if they like and let us know. But in theory, there's no way to free data in the way that you can do it with free in C, where you can just free arbitrary things. If that syscall with a negative number of bytes actually worked, then the only sensible way that you could really do things is to treat it like a stack. You allocate a bit of space, allocate a bit more space, allocate, and you have to remove or free the space in the reverse order to what you built it. So it's not at all like free. Yeah.
Documentation says to call it with a negative value to free it.
Okay, good. All right. Excellent. So you can call it with a negative value to retract something. Does it say anything about whether it checks whether you're outside the range?
No, it simply changes the
Okay. So, I mean, in theory, you've got this giant memory, none of which is in use. You could just pick an arbitrary address in the middle of that and start storing stuff there if you really wanted to, unless the simulator actually checks that. Right, but even so, if you're starting to retract allocated memory by using negative byte quantities, you'd still want to be careful. If you allocate, and then you can't free something in the middle without freeing the thing above it. So, like I said, it's not the same as malloc and free. Similarly, once you've allocated something in this way, there's no label that you can use to refer to it. So whatever, that's the other thing I should have said, this syscall returns a value which is the address of the chunk of memory that was just allocated. Yeah?
Could you explain like the difference between like the memory like get located and they get created by the malloc and the like by the normal way? I mean, what's the difference between them?
And the normal way?
I mean the...
So you're talking about local variables versus malloc variables or something like that. Sure. Local variables are always, in the case of C, notionally placed on the stack. Malloc variables are always in the heap. And the stack and the heap are at totally different ends of the memory. So that's the essential difference. I guess the other difference is local variables are automatically allocated for you when the function starts executing. Whereas malloc ones, it's up to the programmer to create the objects that they need. So, for example, back in this example here, we had to notionally allocate some space on the stack because we were going to have these three local variables. If this was a C function, we wouldn't need to do that. We just define them as local variables, and when the function is invoked, this kind of code is automatically included. All right. So we can try to implement something like malloc using syscall 9 and give it a number of bytes to allocate and get back a result. Now that looks a hell of a lot like syscall 9. So in fact, you're going to see the body of this malloc function that I've written sets up a stack frame, does the syscall, winds back the stack frame. That's all it does. So I've got the code for that here. Oh, see, I'm wishing I could write in C, but unfortunately I have to write in MIPS. Right, so this is a program that kind of does a malloc of an object of size 20 bytes and then prints out the address of that object. Okay, so V0 is assigned malloc. When you assign a value from malloc, the return value from malloc is an address. So we'd be printing out an address here. I then allocate another 4-byte object, get back its address, and then save a copy of it, save a copy of the address, print out the address, and then store something in it and print out the stored address. Okay. So, allocate, take the return value, store it in $A0 and call the print function. So print the value that was returned effectively. Allocate 4 bytes, save a copy of the returned address in $S0 and then put the address of the allocated object into A0 and call print again. So we're going to print out the address that was returned. It's exactly the same as what we did up here. The reason why we're adding this is because we actually care about the address. We want to use the address later. This address here, we just allocated something and we don't care. So when we call this function, it's quite possible that we'll overwrite whatever value is in $V0. So we've kind of lost our pointer, if you like. If you really cared about saving that pointer, because you were going to use it for something, then you might also want to do something like this. save it in one of the S registers, so it's guaranteed to be preserved across that function call. If you don't save it, it's effectively gone. So the reason we save this one, the object, the 4-byte object that we malloced, is that we want to use it later on. So here we're storing a value, so we're loading up the constant 42 into T0, we're then storing the value 42 into the memory cell indicated by the register $S0. That register contains the return address from the call to malloc. So effectively, we've malloced 4 bytes, we've grabbed the return address from malloc via V0, and then we're using it as effectively as a pointer. And similarly, if we want it, so I mean it's it's a little bit silly because we're storing a value and then straight away we're loading it into a register again and printing it out. And you might say, why didn't you just put 42 straight into A0 and do the print? Well, the reason we didn't do that is we want to make the point that you can actually store into this allocated object and then retrieve the stored value back from the allocated object and print it out. Alright, so let's take a look. What have we learned from this? Well, we can see a little bit. So this is the first address that was returned from our original call to malloc. Okay, so that's a memory address, it's a large number, what we do. I guess one thing you want to check, you want to make sure that it doesn't look at all like a stack address. And if we converted it, I've just reminded myself that there's actually a printf function that the shell can give you. Should look vaguely familiar. No? No. Oh well. Remember that the data segment for MIPS programs is somewhere around this region. So we've done a malloc. We've used syscall9 and it's given us an address which looks like it's somewhere near the data region of SPIM. Okay, that's nice. The next address, so remember that we allocated 20 bytes and we then allocated 4 bytes. So what we'd expect is that the next address that we get back from a malloc is 20 more than the first address we got back from malloc, because that would be the starting address of the 20 bytes that we allocated. This would be the starting address of the 4 bytes that follows on from that, and we see that that's true. So it's increased by 20, and the final thing that we see is that value 42. So we loaded up 42, we stored it in the object that we malloced, we then retrieved it from that object and printed it out. So it looks like malloc gave us something that we could use like a dynamically allocated object. Alright, so that's the main program. So the malloc function, like I said, it's kind of a bit trivial. It sets up the stack frame, it makes the system call to syscall9. Notice that when we call this function, we've already got the number of bytes that we want to allocate in the register A0, so we don't need to modify A0 before we make the syscall. So this is going to allocate the bytes. Also, it returns the address of the bytes that we allocate in $V0, which is actually what we need this malloc function to do. So really, it's mainly setting up the stack frame and winding back the stack frame, plus a little bit in the middle that happens to use $A0 as its input, returns $V0 as its output. A0 is already set before the function call, and $v0 is the value that we want to return. So we don't have to explicitly say all that stuff, although I put it there as comments. So that's our simple, crappy implementation of malloc. And just in case you're interested, there was also a function called print, which effectively does this. Once again, you can see we've got the same setup stack frame. The value that we're printing out is passed in the register A0, so that's fine. So we don't need to set it again. We load up the appropriate syscall, and then we do modify A0 to load in a new line character so we can print that out. So as you can see over here, that effectively prints out the value that was passed into the function, but doesn't put a new line afterwards. So then we force out a new line with those three statements. Now, one thing you can see from that is one of the reasons why you can't rely on $A0 holding its value throughout the function. So when I called this function, I gave it a particular value. I used that value here to print it out as a number. I then overwrote that value, the value stored in the register, with a new line character because I wanted to print out a new line character. So if the calling function relied on $A0 still being correct, it would be sadly disappointed when the print function came back. So I pass in a value, print just prints it out, come back, $A0 gone. Well, it's not gone, we know what value it contains. It contains that, but it doesn't contain the value that we passed in. Alright. Okay, so the whole point of this exercise was not to look at the malloc, it was to look at implementing something like calloc. Okay, now remember the way calloc works, you pass in the number of items, you pass in the size in bytes of each item, and then you've got to allocate some memory and set all of that memory to 0. So we got the same old prologue, blah blah blah. Alright, so now what we want is we want to change this. This is just a copy of the previous one. So we're passing in A0 and A1, where A0 is the number of items. And A1 Okay, so syscall 9 expects $A0 to have the number of bytes, and that's not what we've given the function. We've given number of items and number of items per byte, so clearly to get the total number of bytes to allocate, we need to do some multiplication. The other thing that, in order to do that, do we care? I'll assume that it's going to matter if we don't in fact yeah. So obviously, the way I work out the total number of bytes is I multiply the number of items by the number of bytes in each item. Now here I'm assuming that the value is going to fit in a single register, and I don't have to worry about high and low. Alright, one thing to notice, I've just wiped out the number of items that I passed in. If that matters later in the function, and it probably doesn't, then I need to save that restore it if that was really important. Alright, so that's going to allocate, let's say 20 items of 4 bytes each. That'll allocate 80 bytes. Alright? In fact, maybe I do want to be a little bit careful here. So either way, I'm going to wipe out the value of A0. Like I said, if I wanted to save it, I'd need to make sure. But now adding that instruction there, that multiply instruction, I've wiped out the value of $S0. So I'd better make sure that I preserve that. So that would require me to add something like that, push the original value of S0 onto the stack. Right, so S0 tells me the total number of bytes that I'm dealing with. So that's allocated the bytes, and in theory they're full of rubbish. So basically the next step is to write a loop that iterates through and sets each byte or each word to 0. I'm going to be lazy and I'll just go byte by byte. It would be more efficient to go word by word, but this is effectively the way I'm going to handle this. Now, what have we got? So I'm going to use pointer arithmetic effectively. So I'll see that. So V0 is the start address for the chunk that was just allocated, and the end point is going to be the address of V0 and the total number of bytes, which is stored in S0. So I can start at V0 and I can scan through the list of bytes that or the sequence of bytes that I just allocated, and I can set each one to 0 until I reach that point there, and then I can stop. So clearly that involves a loop. Let's assume that I may as well use V0. V0 is not currently being used for anything else, so that's fine. So while V0 is less than end, in fact, why did I have a separate line? In fact, why did I have a separate line there? Because it's so simple. Alright, so V0 is a pointer to a byte. I set the current thing it's pointing to 0, move it to the next byte, move it to the next byte, move it to the next byte, and keep going until I bump into the final address, at which point I stop. So that's going to make sure that I set all of the values in that newly allocated memory to 0. Alright, so we need a label for the loop, and we generally need a label for the end of the loop. And once the loop's finished, we can just exit the function. Actually, and I've just realised, we also need to save a copy of $V0, so because we're about to clobber that. Or alternatively, I could use, rather than using V0, I could use S1 or something like that, or even T1 for that matter. T1, so I'll do that. That's what happens when you make it up on the fly. T1 hasn't reached the end, then do that. Alright, so we got a fairly small self-contained chunk of code, and we know we're not calling any functions, we're not fiddling with any other registers, so it's probably safe enough to do that. Alright, so we set T1 to the start address, and then, oops, what we want to do, we want to make sure that we haven't reached the end yet. Oh, and I think we also need to set up the end address. So let's do end as register T2. Hopefully that's not a problem. S0 is the total number of bytes. Alright. So those two statements there, move V0 to T2, add S0 to T2 will give me the end address of the stuff that I've just allocated. Now I can do this. So if T1 has reached T2, then I'm done. So I can branch to the end of the loop. Otherwise, what do I want to do? I want to treat T1 like a pointer, and I want to store a value of 0 into the object being pointed to. Now in this case, I'm dealing with bytes. So store the value 0 into the memory location that T1 is pointing at. And increment T1 comes down to quite a nice tight loop. And then go back to the start of the loop. Go back to the start of the loop. Alright, so I mean that's the whole loop, so you can see that comes out pretty nicely, quite compact. So, and the reason I can get away with adding 1 here is everything is being done by bytes. If I wanted to do it faster and I wanted to do store word 0, then I'd have to increment by 4 each time. So any questions on that? Set up the start address, set up the end address, and then iterate till the pointer reaches the end address. Store a 0 in each byte and increment the pointer by 1. Right, like I said, all this code ends up in the exercises directory. Anyway, so you can study it at your leisure. Unless you're going to ask me something which you're not. Okay. Oh, no, I forgot to do something. What did I forget to do? Maybe I didn't. Maybe it doesn't matter. Right, there's the print function. Yeah, I forgot to restore S0 at the end of the function because I saved it. Now it might turn out if you go and analyse the code properly, maybe you don't need S0 after all. But let's be safe. Okay, so restore the value of S0 that we saved on the stack, restore the return address, restore the frame pointer, and finish the function. Okay. Right, arrays. You can have named arrays as long as they're part of the data region and as long as you define the names at assembly time. That's how you might do it. An array of 10 int values, or with MIPS you don't know exactly what that means. That could be an array of 10 ints, or it could be an array of 40 characters. Up to you to interpret it how you like. This one pretty much guaranteed to be an array of ints though, because you've initialized it. And they certainly don't look like it's going to be a sensible array of bytes. Cool. Except where did that 2 come from? I don't know. Maybe I used to have a 2 there and I removed it. Alright, so in any case you can initialize arrays like that. You can give names to arrays like that. The way we access the elements in C, we could use an index for I equals 0, I less than n, I plus plus, vec I. Alternatively, I showed you a couple of weeks ago that we could do effectively what we just did on the previous example, was get a pointer pointing at the start of the array and moving it using pointer arithmetic until it reaches the end of the array. So I'd call that a cursor. Right, either way you do it, you need to take account of how large the elements are. If the elements in the array are ints, you've got to keep bumping your values by 4. If the elements of the array are chars, you can bump them by 1. If they're short ints, which might be a half word, you can bump them by 2 each time. When you're passing arrays to functions, in C, all you ever pass is a pointer to the start of the array. And that creates potential problems because you don't know how long the array is. The only bit of information the function gets given is where does this array start. So, 2 ways you can handle that. The way it gets handled for strings is we put a marker at the end of the string so we can scan through and we'll know that we've hit the end of the interesting chars when we see that \0. The other way you can do it is to pass an extra parameter to the function which tells the function how large the array is. Okay. And that sum of example was an interesting example of passing an array to a function. If you went back and look at that, you'd see that we simply load the address of the start of the array, and that's what we give to the function each time. Alright, so here's another example, slightly more realistic perhaps. Got an array of 10 integers, got an index variable, We all know how to do that in C. This is how you'd render something like that in MIPS. Okay? So S0 is going to represent the I register. S1 is going to represent the index 1 beyond the end of the last index. All right, so we go from 0 to 9. If we discover that S0 has reached 10, then we know we're finished. So the reason for doing things that way is because it kind of simplifies the structure of the loop. So all you've got to do is check whether S0 has reached S1, and if it has, you go straight to the end of the loop. If you try to do the test, to render the test like it looks in C, you often end up with having to have a branch that jumps around a single other branch that goes to the end of the loop. But I mean, you can always arrange these things properly, but effectively that's what I've done. So I'm checking whether I is greater than or equal to 10, and if it is, then we're breaking out of the loop. Alright, so at this point, we've got a value for I. I is an index in the range 0 to 9, but that's not going to help us if we just use that as an offset into the array. We need to multiply by 4 so that we, rather than dealing with an index value, we're dealing with a byte offset, which we can then use as a way of accessing a particular element of the array. Okay? So if T0 is 0, then we're going to look at the first 4 bytes of the array. Remember, we're doing a load word here. If T0 was 4, we'd be looking at the second element in the array. If T0 was 8, we'd be looking at the third element in the array. But in those cases, the index values would be 0, 1, and 2. So we need to multiply the index by 4 to get an appropriate byte offset. So that's what those two instructions are doing there. And as I said before, you can probably just stick a 4 there and it'll do the multiplication properly without having to involve T0 in that step. But anyway, so we grab the next element of the array, vec T0, and we store it in the register A0, which is the argument to the print function, and we call the print function, and it prints it out. We then increment the index by 1 and go around the loop again. Now, if you really wanted to, you could do S0 as a byte offset, in which case you'd change a few things. You'd change that to 40. You wouldn't need the multiply anymore, and you could do add I S0, S0, 4, and then use that directly as an index. And of course, having incremented it, we go around the loop again. So where do you do the multiplication by 4? You could do it the way I've done it, or you could do it by, rather than having an index value, by always working with an offset. Now, potentially there's a reason why you want to keep it as an index, is because you want to use that index value for some other purpose. So maybe what we want to do is multiply I times vec of I, in which case you obviously can't replace the index by an offset. So that was using an index. I showed you this technique a while ago, and basically it's the same technique that we just saw in the Kellogg slide. Except that should be a pointer. So current is a pointer to an integer, end is a pointer to an integer, and we iterate through the array by incrementing the pointer to the next element, to the next element, to the next element, until it reaches the end of the array. And we print out the value currently being pointed to on each iteration of the loop. Alright, so loading in the address of the first element in the vector into S0, loading in the address of the last element in the vector. We have to know that there are 40 elements in the vector to do that. If this was maybe inside a function and we were actually passing in the array, then perhaps we would have passed in this value as a second argument, then we'd have to do an add operation to eventually produce this address. I think that was actually what we did in the Kellogg case. Right, so we just iterate as soon as the current address reaches the end address, then we quit. Otherwise, we load up the value that's currently being pointed to into register A0 and pass that to the print function, and then go around the loop again. But before we do that, we need to increment the pointer by an appropriate amount. And in this case, we need to increment it by 4. As I mentioned when I talked about pointer arithmetic in C, C understands that if you've got a pointer to an int and you increment the pointer value, what you want to do is move to the next int in the memory, which means you want to increment the pointer by 4 bytes. Okay. So in MIPS you have to be explicit about that. C understands how to do it because it knows what the size of the various objects are. Don't forget that should have been int star current, because current is a pointer. Alright. If we want to have an array that's local to a function, then we can allocate that on the stack. We've already seen how to do things like how to allocate local variables on the stack before. So basically in the prologue we set up the usual stuff, set up the return address and the frame pointer, and if we want to allocate space for an array, then we simply decrement the stack pointer by the amount of space that the array occupies. And the other thing that we know, having done that, is effectively that the current value of the stack pointer is the address of the first element in the array that we just allocated. So this is going to allocate a local array of size 10, and what we're doing here is we're effectively assigning the start address of that array to the S0 variable, and you can see that we're getting the start address because that's where the stack pointer ends up pointing. Then we do some computation, and we can use $S0 like an address, like a pointer, like we did in the previous slide. And then, of course, at the end, we've got to clean things up. So we decremented SP by 40. At the end of the function, we've got to add 40 on to push it back to where it was, and then we push it up 4 more to get the return address, push it up 4 more to get the frame pointer, and we got the stack pointer back to where it should be. And then we do a jump to the return address. Alright, that will do for today. Next time I'll talk about two-dimensional arrays.